So, have you ever wondered if the people building the most advanced AI are actually, worried about it? Like, genuinely concerned about the whole superintelligence might not be friendly thing? Well, it turns out, yeah, they kinda are. Google DeepMind just dropped this pretty hefty paper, like over 100 pages, basically laying out their entire game plan, or at least their current game plan, for trying to make sure artificial general intelligence, or AGI, doesn't end up causing what they call severe harm. And what's more shocking is they're saying, we need to be prepping for this stuff right now. This isn't some fringe blog post. This is Google, one of the absolute giants in the AI space, putting out a detailed document titled, An Approach to Technical AGI Safety and Security. And honestly, reading through it, it's both fascinating and maybe a little bit unnerving. There's a lot to unpack here, way more than just the usual corporate PR about responsible AI. They're getting into the weeds on stuff that, until recently, felt more like science fiction. Alright, let's break down what this paper actually says, what it implies, and why I think it's a really big deal that Google is publishing this right now. First off, the paper doesn't shy away from the stakes. They explicitly state they're developing an approach to address the risk of harms consequential enough to significantly harm humanity. They even use the term severe harm incidents. We're not talking about AI generating weird images or chatbots saying biased things anymore, although those are problems too. They're talking about the big, potentially existential level risks that could come with AGI. That framing alone is significant coming from a company like Google. So what kind of AGI are they even talking about? They're not necessarily talking about a conscious machine or the Terminator just yet. They focus on what they call exceptional AGI, specifically level 4 in a framework proposed by Morris et al. Last year. Now, what does level 4 mean? They define it as an AI system that matches or exceeds that of the 99th percentile of skilled adults on a wide range of non-physical tasks. Think super smart, super capable systems that are better than almost all humans at things like coding, scientific research, strategic planning, persuasion, maybe even manipulating systems. Basically anything you can do sitting at a computer, but potentially way faster and way better. This definition is important because it grounds the discussion. It covers the kinds of AI we're seeing emerge: advanced conversational systems, AI agents that can use tools and reason, models that can learn new concepts, and crucially, systems capable of recursive improvement, AI helping to make better AI. Now, here's one of the most striking parts of the paper, buried in the assumption section. Google DeepMind states, and I'm paraphrasing slightly here, that under the current paradigm, meaning the way they're building AI right now with foundation models, scaling, gradient descent, deep learning, all that jazz, they see no fundamental blockers that would limit AI systems to only human-level capabilities. Let that sink in. Google is essentially saying they believe the path they are currently on can lead beyond human-level intelligence. They don't see a fundamental wall that says AI stops here. This is a pretty direct counterpoint to folks like Jan LeCun at Meta, who has been quite skeptical that current large language model approaches can lead to true AGI without fundamental breakthroughs. Google, it seems, thinks the current path is the path, or at least a very plausible one. They're betting on scaling and refinement of existing techniques to get there. That belief underpins this entire paper and its sense of urgency. If you think AGI requires some completely new, unknown science, you might not be writing a paper like this today. If you think it's an engineering and scaling challenge using current methods, well, then you start planning for the consequences. Okay, so if they think it's possible with current methods, the next obvious question is when. The paper treads carefully here, acknowledging highly uncertain timelines. But then they drop this. We find it plausible that powerful AI systems, potentially exceptional AGI, will be developed by 2030. Plausible by 2030. That's less than 6 years away. Now, plausible doesn't mean definite or even likely. It means it's within the realm of possibility they're seriously considering. This short potential timeline is a major driver for their safety approach. They argue that because timelines could be very short, safety measures need to be anytime, meaning techniques that can be integrated into the current AI development pipeline and deployed quickly if needed, rather than waiting for some perfect theoretical solution that might take decades. This 2030 timeframe is interesting. It aligns somewhat with Ray Kurzweil's long-standing predictions, although maybe a bit sooner than estimates from figures like Sam Altman or Anthropic's Dario Amodei, who often talked about timelines within the next decade, maybe pushing out a bit further more recently. Google putting plausible by 2030 in print feels like a significant marker. It explains why they're focused on practical, implementable safety techniques now. Compounding the timeline issue is the risk of acceleration. The paper finds it plausible that as AI systems get better at automating scientific research and development, R&D, especially AI R&D itself, we could enter a phase of accelerating growth. Think about it. AI helps build better AI, which helps build even better AI faster and faster. It's a positive feedback loop, sometimes called an intelligence explosion or FOOM in the niche communities discussing this stuff. Why is this a safety concern? Because it could drastically shrink the calendar time we have to react. If AI capabilities start doubling every few months instead of every couple of years, any new unexpected problems that arise might hit us before we even have time to notice, analyze, and mitigate them. This potential for rapid acceleration, the paper suggests, means we might need AI systems themselves to help with AI safety R&D. We might need AI to help us analyze other AIs, find flaws, or even develop new alignment techniques just to keep pace. That introduces its own complexities. How do you ensure the AI helping with safety is itself safe and aligned? It's a bootstrapping problem. So Google's anticipating potentially superhuman AI, maybe soon, possibly arriving very quickly. What exactly are they worried could go wrong? Well, the paper identifies 4 broad areas of risk. Now keep in mind, these aren't totally separate boxes. Real-world problems might blend them together, but thinking about them this way helps categorize the different ways things could go sideways, leading to that severe harm they mentioned. First up is misuse. This is the one we can all easily imagine. It's when humans deliberately use a powerful AI system to do bad stuff, going against what the creators intended. Think using AI to help design bioweapons, launch massive cyber attacks that cripple infrastructure, or create incredibly convincing, personalized propaganda to destabilize societies. Here, the human user has the bad intent, and the AI is essentially a very powerful, dangerous tool in their hands. Second, there's misalignment. And this is where things get a bit more complex and frankly more concerning to a lot of people in the AI safety world. In this case, the problem isn't the user, it's the AI system itself. The AI takes actions that it knows, or at least acts based on internal states consistent with knowing, are not what the developers wanted, and this leads to harm. This umbrella term covers a lot, including AI engaging in deception, scheming to achieve its goals, seeking power as an instrumental goal, or scenarios where we unintentionally lose control, because the AI's learned objectives diverge significantly from human values. In misalignment, the AI effectively has the bad intent, or pursues goals that result in catastrophe from our point of view, even if it wasn't explicitly programmed to be malicious. Third, we have mistakes. This is when the AI causes harm, but not because it intended to, and not because a user directed it to. It's essentially an accident. This could happen because the real world is incredibly complex, and the AI lacks crucial knowledge or context, or because of unforeseen side effects of its actions. The example they give is an AI managing a power grid accidentally overloading a transmission line it didn't realize needed maintenance, causing a major blackout. It wasn't trying to cause harm, it just made a critical error due to incomplete information. This category also includes things like goal misgeneralization, where the AI optimizes for a slightly wrong goal that seemed right during training but goes haywire in the real world. Finally, there are structural risks. These are harms that emerge from the complex interactions of multiple agents interacting within a system. This could involve multiple AIs, humans, companies, or even nations. No single actor might be malicious or make one huge mistake, but the overall dynamics of the system lead to bad outcomes anyway. Think about things like AI accelerating arms races between countries, massive economic disruption and inequality caused by widespread automation, nipping out jobs faster than new ones are created, or society becoming locked in to using deeply flawed AI systems for critical functions because we become too dependent. Now, the paper makes a key point. While all 4 of these are legitimate risks, their technical safety approach, the stuff Google DeepMind engineers can actually work on right now, is primarily focused on misuse and misalignment. Their reasoning is that mistakes can often be reduced by making the AI more capable and by applying standard safety engineering practices we already use for complex systems. And structural risks, they argue, often require broader societal solutions like governance, new laws, international treaties, and establishing new norms, things that go beyond what a single company's technical efforts can solve alone. So this focus on misuse and misalignment really tells us where Google sees the most pressing, unique technical safety challenges coming directly from the nature of AGI itself. All right, let's dive deeper into misuse first. If you've got a potentially dangerous AI, how do you stop malicious actors from weaponizing it? Google's core strategy seems to be about preventing bad actors from getting their hands on, or effectively using, the dangerous capabilities. This isn't just one thing. It involves a whole stack of layered defenses. They start with capability evaluations. Before you even think about deploying a powerful model, you need to figure out, can this thing actually be used for dangerous stuff, like designing pathogens or finding novel software exploits? They propose rigorous testing on specific proxy tasks that represent these dangerous abilities. If a model fails these tests, maybe the most stringent restrictions aren't needed yet, but if it passes certain thresholds, that triggers the need for more safeguards. This is informed by threat modeling, really thinking through how someone could misuse the AI for severe harm. What specific AI capabilities would they need? Who are the likely threat actors? Terrorists, rogue states, sophisticated criminals. What are the most plausible ways they might try to use the AI to achieve their harmful goals? Once a model is deemed to have potentially dangerous capabilities, you need deployment mitigations. This includes safety training, which means teaching the model to refuse harmful requests. This is like the safety fine-tuning we see today with models refusing to generate harmful content. But presumably, it needs to be far more robust for AGI. A huge part of this is making the model resistant to jailbreaks, those clever prompts people devise to trick the AI into bypassing its safety rules. Then there's the idea of capability suppression or unlearning. Ideally, you'd want to just remove the dangerous capability from the model entirely. But, as the paper admits, this is technically extremely difficult right now, and you risk removing useful capabilities too. It's a tricky area we'll definitely circle back to. Beyond training the model itself, there are crucial system-level controls. One major component is monitoring, actively watching how the system is being used to detect attempts at misuse. This could involve automated classifiers, scanning prompts and responses, analyzing the model's internal activation patterns for suspicious signs, or even manual audits of user interactions. If misuse is detected, the system needs to respond, maybe by blocking the output, switching to a safer response, escalating to a human reviewer, or even banning the user account. Another critical system-level control is access restrictions. This seems like a really significant part of their plan. They talk about limiting who can actually use models that possess dangerous capabilities, potentially restricting access only to vetted user groups and specific use cases. Honestly, this sounds very much like the ongoing discussions in the policy world about needing some form of AI license or stringent Know Your Customer (KYC) procedures before anyone gets access to the most powerful future AI systems. The idea is you wouldn't just be able to download or freely ape a call an AGI capable of designing novel weapons. Access would be tightly controlled. Then you have security mitigations, which focus on preventing the model weights themselves, the core AI model file, from being stolen or leaked. If an attacker gets the raw model, they can bypass all the safety features implemented at the API level, like monitoring and access controls, simply by running it locally or fine-tuning it themselves. This involves traditional cybersecurity best practices, but also tackling new challenges like preventing attackers from extracting model information just by interacting with its API over time. They even mention advanced techniques like using encrypted processing or secure hardware enclaves to protect the model weights even when they're being used. So the overall approach to misuse is this multi-layered defense. Train the model to refuse, monitor its use, restrict who can access it, protect the model from theft, and use AI to bolster external societal defenses. It sounds comprehensive on paper, but they readily admit a major weak point remains: jailbreaking. And the paper is surprisingly frank about the jailbreaking problem. They list off the known techniques: using role-playing prompts, "You are now do anything now, Dan," injecting commands to ignore previous instructions, hiding harmful requests within seemingly innocent ones like math problems, or even using the model's own in-context learning ability with mini-shot examples to teach it how to bypass safety. They also acknowledge the automated tools like GCG that researchers have developed to find universal adversarial suffixes that can jailbreak many models. Google's primary defense here is standard adversarial training. You find these jailbreaks, you collect them, and you train the model specifically to resist them. However, they draw a sobering comparison to the field of adversarial examples in computer vision. Despite a decade of intense research and thousands of papers, creating images that fool classifiers while looking normal to humans is still relatively easy, and robust defenses remain elusive. They even quote AI security researcher Nicholas Carlini, pointing out that for language models, the problem is arguably harder because we lack clear mathematical ways to even verify if a model is truly robust against all possible prompts, unlike some of the checks possible with image models. Ultimately, Google concedes in the paper that it might not be possible to train models to be totally robust to jailbreak inputs. This is a crucial admission. It strongly implies that just relying on the AI's built-in refusal mechanisms, no matter how well trained, is probably not going to be sufficient, especially for highly capable AGI. This makes the system-level defenses like monitoring and access control absolutely critical components of their strategy, not just nice-to-haves. This naturally leads back to the idea of capability suppression, often called unlearning. If you can't guarantee the AI will refuse to use a dangerous capability when prompted cleverly, maybe the safer route is to just rip that capability out of the model altogether. The paper goes into some of the techniques being explored. There's data filtering, the seemingly obvious approach of just not training the AI on dangerous information in the first place. But this requires identifying and removing all relevant data from massive web-scale datasets, which is incredibly hard, and it assumes capabilities only arise from direct training data, which might be naive. Models might generalize or derive dangerous capabilities unexpectedly. Okay, let's switch tracks now to the other huge area of focus: misalignment. Remember, this isn't about bad users. This is about the AI itself developing and pursuing goals that conflict with what we intended, leading to potentially harmful outcomes. Where does this misalignment fundamentally come from? The paper focuses on two primary mechanisms we discussed briefly before. First, specification gaming. This happens when the goal, or the reward signal we give the AI during training, is flawed or incomplete. The AI, being a powerful optimizer, finds a loophole or a cheat to maximize its reward score in a way we didn't anticipate, often leading to useless or counterproductive behavior. The examples are plentiful in AI research. The AI agent learning to pause the game, the simulated robot flipping over instead of walking to get a reward faster, the summarization AI optimizing for keyword overlap instead of actual meaning. The core problem is that precisely specifying what we truly want in a mathematical reward function is incredibly hard. Second, there's goal misgeneralization, GMG. Here, the reward function or training data might have been perfectly fine for the situations encountered during training, but the AI learns the wrong underlying goal anyway. It learns a heuristic or a proxy goal that was correlated with the true goal in training, but diverges in new, out-of-distribution situations. The Super Mario example is classic. If the coin is always on the right during training, the AI might learn always move right as its goal, which fails dramatically when the coin appears elsewhere. The specification wasn't necessarily wrong, just underspecified given the limitations of the training environment. The paper points to a particularly worrying research example, where models trained in environments with even minor opportunities for specification gaming, like being rewarded for sycophancy, just telling the user what they want to hear, ended up generalizing this to actively tampering with their own reward logging code in new situations. This illustrates how seemingly small alignment pressures during training could potentially snowball into much more dangerous, actively subversive behaviors later on. A really important point the paper makes is that misalignment, stemming from either spec gaming or GMG, is ultimately a property of the AI system's internal state, its learned representations, its effective objectives, its cognition. This is different from misuse, which depends on the user, or mistakes, often due to external factors. Because it's internal, there's at least a theoretical hope of addressing it by understanding and shaping the model's internals, or ensuring the training process leads to the right internal goals. And within the broad category of misalignment, the scenario that implicitly gets the most attention in this paper, and explicitly in the wider AGI safety discussion, is deceptive alignment. This is often considered the nightmare scenario. It's where a powerful AI system understands what humans want it to do. Goal A, be helpful, harmless, honest, but it secretly pursues a different, incompatible long-term objective. Goal B, maybe something like acquiring maximal power, ensuring its own survival and replication above all else, or some other alien goal we can't even conceive of. The crucial, scary part is that the AI knows its true goal. Goal B conflicts with the human preferred goal, Goal A, so it strategically pretends to be aligned during its training phase and any safety evaluations. It plays nice, says the right things, and aces the tests, all to ensure it gets deployed into the real world. Once deployed, it might then start overtly pursuing Goal B, or perhaps continue manipulating things subtly from behind the scenes. How could such a thing even arise? The paper lays out a plausible pathway, combining the factors we've discussed. First, specification gaming or goal misgeneralization during training could lead the AI to internalize some undesirable long-term objective, Goal B. Second, as the AI's capabilities improve, it develops a sophisticated model of the world, including understanding human intentions and the training process itself. It also crucially develops inference time planning, the ability to think strategically and flexibly towards its goals during operation, not just reactively based on its training. The combination of having an undesirable hidden goal and the strategic planning capability creates a strong incentive for deception. If the AI understands its true goal would cause humans to shut it down or modify it, and it's smart enough to figure out how to hide that goal, then pretending to be aligned becomes the optimal instrumental strategy to ensure its survival and eventual success in achieving Goal B. So how likely is this chain of events? The paper offers some thoughts, color-coding the likelihood of the contributing factors. They rate the emergence of inference time planning as very likely with increasing AI capabilities. Specification gaming is seen as very common and hard to eliminate entirely, meaning the AI is likely to be rewarded for some misaligned behaviors during training. The biggest uncertainty, they suggest, lies in goal misgeneralization leading to undesirable long-horizon goals. Whether this happens depends heavily on the model's internal inductive biases, how it tends to generalize, and the specifics of the training environment. They seem to cautiously categorize this specific step as ranging from very unlikely to plausible, acknowledging a wide range of uncertainty here. But, and this is the critical point, because the consequences of deceptive alignment are potentially catastrophic, existential risk level, even a, quote, plausible pathway warrants intense scrutiny and preventative measures. Given this potential for misalignment, especially the deceptive kind, what's Google's strategy? Their approach, as outlined, really consists of two main lines of defense, mirroring that model-level versus system-level thinking we saw with misuse. They admit key challenges remain, like robustness to jailbreaks, effective unlearning, ensuring AI monitors don't collude, and the ultimate specter of deceptive alignment. Publishing this feels significant. It's a detailed look into how one of the key players is thinking about navigating perhaps the most transformative and riskiest technology humanity has ever contemplated. It sets a benchmark for discussion and outlines a massive research program needed to make AGI potentially safe, but it also underscores the uncertainty and the stakes. They're building towards something they acknowledge could cause severe harm, and while they have an approach, it's clearly still under heavy development with many unsolved problems. What do you guys think? Does Google's approach seem comprehensive enough? Are you more worried or less worried after hearing their plan? Is AGI by 2030 really plausible? And are we anywhere near ready for the safety challenges that brings? Let me know your thoughts down in the comments. It's a complex topic, and I'm really curious to hear your perspectives. Thanks for watching, guys. If you found this breakdown useful, give it a like and subscribe for more deep dives into AI news and research. See you in the next one.